Iowa State University. My
Oh,
name is
hi, Martin. Martin, wait a little bit time. Yeah.
Oh, okay.
He didn't start. Yeah. Now, okay.
Welcome to ICANX Talks, Connecting the World and the Universe. My name is Martin Thuo. I'm coming to you from Iowa State University in the middle of the United States. I'll be your moderator, assisted by Ms. Kim from SKKU University. Our speakers today are going to be Sihong Wang from University of Chicago and Sejeong Kim from the University of Melbourne. And first, we'll have Sejeong Kim from University of Melbourne. A little bit about Professor Kim. She is an assistant professor or lecturer at University of Melbourne in Australia. She works on 2D materials for integrated quantum physics. She got her bachelor's degree from Sejeong University and a PhD from KAIST in Korea in 2014, followed by a research fellowship at University of Technology in Sydney from 2017 to 2020. She has many awards, and one of which is the ICANX Young Scientist Award, and that's why she's giving us our talk today. She has been named Best Emerging Scientist in photonics and quantum electronics. She has been named or awarded for being an excellent young scientist in 2018. She was selected as 30 Rising Star by the Optics Society of Korea and serves on the editorial board of APL Photonics. She has many publications in very good journals like KCS Nano and Nature Materials. And I can spend a lot of time talking about her, so I'll let her tell us about her work in 2D materials for integrated quantum photonics. Professor Kim?
Let me share my slides.
Yep, sure.
Can you see my slide?
Yep.
Okay. So thank you for the introduction. It is an honor to present my work at ICANN Talks and also starting Chinese New Year by giving a talk here. So today I will discuss how hexagonal boron nitride and how it's been used for integrated quantum photonics. So before I begin, here I prepared photos of University of Melbourne. I started my research group a year ago, and before that I worked at University of Technology Sydney at Igor Aharonovich's group. So today's presentation highlights research projects mostly done when I was at UTS. And without further ado, let's look at what are photonic integrated circuits and quantum photonic integrated circuits are. So photonic integrated circuits are frequently imagined as a new sort of microprocessor that uses photons instead of electrons to perform the same functions as conventional microprocessors. And one of the primary motivations for developing a photonic integrated circuits is to overcome the Moore's law limit. And photonic devices will enable us to develop high-speed, energy-efficient, and computing or communication devices. So photonic integrated circuits require multiple photonic components, including waveguides and couplers and modulators and so on. And since the majority of these components can be made from silicon or silicon-based materials, photonic integrated circuits takes advantage of using well-established manufacturing protocols and facilities in semiconductor electronics. Meanwhile, we are trying to develop quantum photonic integrated circuits, which have different material needs than the prior ones. Just a short note that there are 2 review articles from 2020 published on this topic, the titles of which I copied and pasted on the right-hand side. So quantum photonic integrated circuits is basically a quantum information processor that provides implementation paths for all of the essential areas of quantum technology, such as quantum communication, quantum computing, and quantum sensing. Therefore, it must generate and modulate and detect the quantum light source. And there are essential components for quantum photonic integrated circuits, which lists are shown here. So the first essential component is single photon sources that are ideally produce 1 photon per excitation pulse. And the second one is efficient and fast single photon detectors. And we also need actively controllable photonic elements. Of course, we also need waveguides and quantum memories that enables photons to be stored and retrieved. We also need wavelength conversion element. And finally, single photon nonlinearities for photon-photon interaction. In general, quantum circuits present a greater technical challenge than photonic integrated circuits. And majority of essential components are at their early stages. So we will focus on, and in this talk, we will focus on single photon sources and waveguides. Then our research question is, what material can generate single photons? As a matter of fact, numerous solid-state materials are capable of generating single photons. For example, epitaxially grown quantum dots, such as indium arsenide and gallium nitride, can generate single photons, as well as colloidal quantum dots that are created chemically. In addition, defect in crystals, so-called color centers, are also source of single photons. For example, diamond and silicon carbide are two materials that are widely utilized in this category. And although we have a library of materials to choose from, researchers are constantly searching for nearly ideal single photon sources, as well as developing existing ones. Then what is ideal single photon source? Like a few years back, Reimer and Scher compiled a list of requirements for ideal single photon sources that is published in Nature Photonics. So first, an emitter should emit single photons on demand with a vanishing probability of multi-photon emission. And second, once a photon has been emitted, it should be collected with high efficiency. And third, each photon should be identical in every way, including wavelengths, polarization, and spatial and temporal profiles. And aside from these fundamental needs, there is a wish list that includes things like a high repetition rate, tunable emission wavelengths, and electrically triggered operation. At the time, there was no clear winner among all the possible materials for an ideal single photon source. And as a result, researchers will continue to hunt for new material platform while also developing pre-existing material platforms. The new material that captured researchers' attention was 2D materials. What made them prevalent in the lab was the easy fabrication method to get monolayer samples. One can produce 2D monolayer by just exfoliating layers from bulk crystals with a sticky tape. Apart from that, due to its atomically thin nature, it can be transferred to various photonic devices without degrading original quality. And additionally, heterostructures are possible with different two-dimensional materials, regardless of the lattice mismatch. As a result, some researchers came up with the idea of creating a single photon emitter from 2D materials. And coincidentally, 5 papers released in 2015 and reported the first single photon emission from tungsten diselenide. However, one of the drawbacks was that this emission could be only observed at cryogenic temperatures. In the following year, in 2016, the first room temperature emission from two-dimensional material was reported by using the material called hexagonal boron nitride. In this case, room temperature operation was possible because HBN has a very wide band gap, as illustrated in this diagram. And this facilitates two-level system deep within the band gap. This indicates that if you consider the thermal energy at room temperature, which is around 25 millielectron volt, and that energy is insufficient to move the electron in the excited state to a higher state. Therefore, our group focused on hexagonal boron nitride as a promising candidate material for next generation single photon sources. And here's a brief introduction of HBN. So hexagonal boron nitride is a 2D material that contains boron and nitride atoms arranged in hexagonal pattern. And it has a very wide band gap again, which corresponds to 6 electron volt. And brief history of HBN is that for more than 70 years, HBN was used as a thermally stable ceramic material. And then, as we know, HBN has been employed as an ideal substrate for graphene. Then now HBN is rising as an interesting material in its own right, facilitating research into quantum optics, photon polaritongs, and UV emitters. And this slide briefly summarized the experimental result obtained with hexagonal boron nitride. After annealing the material at a high temperature, we can see bright emissions in this PL scanning image. And then we analyze these bright spots in further detail using a spectrometer, revealing a sharp peak around 630 nanometers. And the signal here is sent to the Henry-Brown twist setup, abbreviated HBT setup, which is capable of analyzing anti-bunching of photons. And this is the second order correlation graph. This shows, this clearly displays the deep when the delay time is 0, verifying the single photon nature. And although this new quantum emitter was discovered relatively recently, we were able to identify a number of favorable features. For example, HBN single photon emitters are very bright and exhibit stable optical emission, even up to 800 Kelvin. Additionally, the emitter shows a high degree of purity, implying that the probability of observing multiple photons is extremely low. And next, it is important to integrate the single photon emitters into integrated photonic circuits. The first step is to couple a single photon emitter to photonic waveguide. And apart from that, apart from waveguide integration, integrating emitters to photonic cavities is also essential because it is expected to mitigate some of the issues encountered with solid-state quantum emitters, for example, limited light extraction efficiency and phonon-induced dephasing. And here, when we integrate these two systems, the integration approach can be either monolithic or hybrid. The term hybrid system refers to a system in which the light-emitting material and the cavity are made from different material. For example, if we use HMAN quantum emitters, then waveguide or cavity can be made of silicon nitride. And meanwhile, a monolithic system requires only one material. For example, if we are using HBN emitters, the cavity or waveguide is also made from HBN. And this slide is discusses further on the light and matter coupling and the challenges. So to engineer the emission property of quantum emitters, we should be able to modify the density of state at the transition frequency. And this is where the optical cavity comes into play, enhancing the emitter's spontaneous emission rate. The increased rate of spontaneous emission is referred to as Purcell effect. And to create a system in which light and matter are coupled, 3 requirements must be met, which are spectral matching, spatial matching, and polarization matching. And in this section, I will only discuss spectral and spatial matching. The term spectral matching, or it can be also called wavelength matching, refers to matching of the quantum emitter's wavelengths with the cavity resonant wavelengths. And meanwhile, spatial matching refers to the emitter's location relative to the optical mode's maximum intensity. And let's take a look at the side cross-sectional view of this system. And due to the fact that 2-dimensional material are transferred to photonic cavities, the emitter in 2-dimensional material is coupled to optical mode only via evanescent field, and this can be problematic. To overcome the problem, what we proposed this idea of creating monolithic device with 2D materials. So previously, 2D materials were transferred to optical cavity in order to exploit the cavity effect. However, how about we just fabricate 2D crystals to create photonic devices? In that case, we can eliminate the transfer step, which is typically regarded as a not ideal technique for mass production. And moreover, single photon emitters can now be contained within the material, ideally coupling to the optical field maximum. So in 2018, we demonstrated all 2-dimensional material photonic devices for the first time. And by using conventional electron beam lithography, we created photonic components, including photonic crystal cavities, microrings, circular Bragg grating cavities or bullseye cavities, and grating couplers. And from next slide, I will first review the research work on waveguide integration before moving on to cavity integration. The experimental demonstration of waveguide integration has a relatively short history. So the first single photon emission from a layered material coupled to an on-chip waveguide was reported in 2017 by Tondorf and Brachich in Nano Letters. They reported single photon emitters in layered gallium selenide coupled to silicon nitride photonic waveguide. And this experiment was conducted at 10 Kelvin. And it says September 2019, Paskins and his team reported the integration of WSE2 monolayer onto silicon nitride chip. And single photon emission have been validated. In this case, again, this measurement was conducted at cryogenic temperature. In the same year, in 2019 and same month, we also reported a system of quantum emitters embedded in hexagonal boron nitride here, coupled to an on-chip waveguide. The single photon emission from an emitter at position A, shown here, was coupled into a waveguide and subsequently scattered into free space by the grating coupler in position B. We took an advantage of HMAN stability at room temperature. Therefore, all these measurements were taken in ambient condition and at room temperature. So this was the first demonstration of 2D quantum light directed into waveguide at room temperature. Another highlight of last year is the experimental work by Erando Herrans and the team. In this case, single photon emitters in WSE2 were resonantly excited and coupled to a waveguide, and the measurement was conducted at cryogenic temperature. And last year, August, we also successfully demonstrated the monolithic system for the first time. In this case, the waveguide is now made of HMAN crystal and contains HMAN single photon emitters. Because we are using monolithic approach, we can simplify the fabrication process by eliminating a line transfer step. And SEM images of HMAN monolithic waveguide is shown here with a slot waveguide at the center. This monolithic approach allows for a high ammeter to waveguide coupling efficiency defined as beta here. So from left to right, the schematic shows nanocrystal on a waveguide, a 2D monolayer on a waveguide, and a monolithic waveguide with a light emitter embedded. As you can see, the monolithic approach here can achieve a coupling efficiency of more than 3 times than the other configurations. In the PL map shown here, a single photon emitter is positioned at the center of the HMAN waveguide, which we refer to as SPE. And this emission is coupled to waveguide and scattered by gradient coupler at C1 and C2 position. And this data shows spectra collected directly from SPE with an inset G2 correlation measurement. And we observed the same peak in PL spectrum when we collect the emission from position C1 and C2. The single photon characteristic is remained as seen in this inset. Aside from waveguide integration, again, cavity integration has been explored, and coupling quantum emitters into cavity mode is more challenging task. And one of the biggest challenge in the spectral matching here between the cavity mode and the emission wavelengths, if you look at the HMAN emitters wavelengths, once we create HMAN quantum emitters, emission wavelengths can be anywhere in the visible wavelengths, which makes it difficult to match with the cavity mode. So to overcome this problem, eventually we need to be able to find a way to create emitters with fixed wavelengths or to tune the wavelengths. By the time when we started this research, we began this experiment, and the wavelengths of quantum emitters were still random. So in 2018, we demonstrated the first HMAN monolithic photonic crystal cavities as shown here. This is SEM images showing one-dimensional photonic crystal cavities made of HMAN only. The optical mode has Q factor up to 2000, resulting in narrow line width here in the spectrum. And HMAN emitters typically have a broad line width at room temperature as shown in this green shaded area. And now to achieve emitter and cavity mode coupling, 2 requirements must be met, again, spatial matching and wavelength matching. And we can tell from the spectrum shown here that wavelength matching wasn't successful at this point. And the outcomes that we commonly look at as a result of coupling are lifetime reduction and increased PL. And in this work, we did not see any brightness enhancement or lifetime reduction since the emitter and the mode were not coupled. And 2 years later, 2020, we were finally able to couple emitters to the cavity mode. The bright spot here is the emission from single photon emitter sitting exactly at the center of the photonic crystal cavity. In this work, we are at the bad emitter regime, which means that the quantum emitter has broader line width than the cavity. And in these spectra, optical cavity mode shows a peak with a very narrow line width and a fixed wavelength. And still, the tuning and detuning the emitter wavelengths to the cavity resonance is still necessary. In this work, we tracked the spectrally jumping emitter, which allowed us to observe the intensity enhancement as shown in the second graph. We can see that when the wavelengths of emitter approaches to the cavity resonance, the PL intensity increases. In this work, we couldn't observe the lifetime reduction of the emitter yet. And to observe the lifetime reduction, we need a proper tuning of a cavity mode. And cavity tuning and the lifetime reduction is very recently demonstrated at the end of last year. So in this work, HBM monolithic photonic crystal cavities with Q factor of up to 5,000 is employed. And to couple the single photon emitter to the cavity resonance, the method that we used is the gas condensation tuning approach. And for this purpose, ambient air was delivered to the cavity at the cryogenic temperature. And this increases the effective size of the resonator, and that caused the cavity mode here, C0, to redshift. And we were able to tune the wavelengths of C0 up to 10 nanometers in this effort. As we gradually tune the resonant wavelengths as indicated as C0 in this figure, the cavity mode eventually crosses the wavelengths of the single photon emitter. And when they finally coupled, the enhanced PL intensity is observed. And finally, by comparing the lifetime of the emitter when it is on and off the resonance, we could derive the Purcell factor of 15. And as discussed earlier, we might be able to find the breakthrough if we can create an emitter with a fixed wavelength. And one of the discoveries in 2020 is that the boron vacancy in HBN has consistent PL emission around 800 nanometers. So we decided to use this PL emission to integrate with photonic cavities. In this work, bullseye cavities are patterned onto HBN crystal. The left image is from optical microscopy. You can see the HBN crystal here. The right one is from SEM image. And after nanofabrication, the entire sample was homogeneously irradiated with focused ion beam to generate boron vacancies. And now we compare PL intensity from the center of the bullseye cavity and outside of the cavity. And we can see PL enhancement as in the blue curve. And this enhancement is due to the cavity effect that increases the emitter's decay rate. This is FDTD simulation result. In addition to that, bullseye cavity has directional cavity mode, which is seen in this cross-sectional intensity profile, also in far field pattern. And this directional emission is experimentally verified as well, as shown here. To summarize my first part of the talk, very briefly, so HBN single photon emitters can operate at room temperature, and monolithic photonic devices are successfully fabricated for the first time. And quantum emitter, HBN quantum emitter and photonic waveguide coupling is demonstrated, as well as the cavity coupling. And for the next few slides, I'd like to briefly introduce our recent research papers. The first one was published in last year, and is titled as a single chiral nanoparticle induced valley polarization enhancement. And to put valleytronics in a nutshell, if we excite WSE2, for example, with right-handedness circularly polarized light, the PL of WS2 also has right-handedness and vice versa. And this is due to the two valleys in the momentum space, which preserves the opposite handedness. Therefore, it enables us to selectively excite one of the valleys by just using the circularly polarized light. However, in reality, this experiment is not obvious for observing the clear difference in the PL intensity. And here is why. If we excite one specific valley using a laser, then the exciton is created. However, due to the phonon-mediated scattering process, the electrons are redistributed, which result in observing PL from both valleys. And therefore, the easy solution is to create a temperature, to decrease the temperature and reduce the number of phonons in the host crystal. And as shown in this figure, PL intensity difference between right-handed and left-handed circularly polarized light, also called as valley contrast, increases as the temperature declines. And this means that the redistribution of electrons is suppressed due to the lack of phonons. However, for practical valley devices, it would be ideal to develop a device which operates at room temperature. And for that purpose, we can take advantage of accelerated spontaneous emission rate. If the spontaneous emission decay process is faster than phonon decay time, then the valley polarization can be preserved even at room temperature. So in our work, we also took advantage of fast spontaneous emission rates due to the plasmonic effect. In addition to that, we utilize Chiron nanoparticles so that we could enhance the valley contrast further. The blue shaded area here is the monolayer WS2, and the black small dots are single Chiron nanoparticles. And polarization resolved PL emission from WSE2 sample without any particles is measured first under the room temperature and ambient condition. The same sample with nanoparticles on top is also measured. And notably, the valley polarization is dramatically enhanced by a single Chiron gold nanoparticle exhibiting the strong selective response of Chiron gold nanoparticle upon circularly polarized light. In this experiment, an important figure of merit is a degree of polarization, which is normalized PL intensity difference. In this work, a large degree of circularly polarization of up to 0.45 from a monolayer WS2 is measured. The second paper was I'd like to highlight is published at the end of last year, 2 years ago. The title is Versatile Direct Writing of Dopamine in Solid State Host through Recoil Implantation. As we previously discussed, a technique which can generate emitters at desired location is a crucial technique. For example, like an array. In this case, the substrate is typically wide bandgap materials such as diamond, silicon carbide, or gallium nitride. And the emitter are defects and impurities such as nitrogen vacancy or silicon vacancies in diamond. Then let's have a brief look at how we can generate these defects conventionally. So conventionally, ion implantation is used for this purpose. Let's have a close look at the nitrogen vacancy center in diamond. It has one vacancy and one nitrogen atom in the carbon site. To create NV centers, we can prepare diamond substrate and implant nitrogen species. Then nitrogen atoms are implanted and some vacancies are also created. And then after annealing the sample at high temperature, it forms optically active defect centers. And now moving on, how can we use this implementation method to create emitters in such an array? For example, to do that, we have to make opening using PMMA, for example. However, and then you need to use implantation. However, this method always requires an implanter, which is a bulky equipment, and additional e-beam lithography to create an opening in PMMA. Therefore, our research question was, is there a method to create emitters deterministically in an array in the lab without any implanter. So this paper shows the answer to that question. And here's the brief explanation of the idea. First, we prepare the substrate, for example, diamond, or it can be any substrate, and then deposit a film such as silicon, and then use focused ion beam to create a pattern. In our experiment, xenon focused ion beam is used. So xenon ion hits the silicon atom, which result in some silicon atoms and xenon atoms in the diamond substrate. Therefore, now any research group that has focused ion beam in the lab can create color centers in diamond. And also by just changing the film material by deposition, you can create various emitters in the substrate. And here we tested 4 different film materials, and they all created optically active color centers as shown in this image. And the spectrum of each emitter matches the known spectrum shapes in previous literatures, and we were also able to demonstrate the emitters in an array. So this was the last slide. And finally, I'd like to thank all my previous group members and supervisors and all the collaborators. And I'd like to thank everyone for listening to my talk. And I'm happy to answer my questions at the end of the session. Thank you.
Okay, great. So I'm sorry. So I take my privilege to introduce Professor Sejeong Wang, our next speaker. So Professor Sejeong Wang is one of the ICANX Young Scientist awardees. That's why he's here on the stage. And Professor Sejeong Wang is an assistant professor in the Prater School.
Hello, Miso, please go ahead. Okay.
Yeah.
Okay, so should I start now?
Mm.
Okay, so I take my hi everyone. This is Miso Kim from Sungkyunkwan University, South Korea. So I will take my privilege to introduce Professor Sejeong Wang, who is one of our ICANX Young Scientist awardee. I'm very pleased to introduce Professor Sejeong Wang, and Sejeong Wang is an assistant professor in the Prater School of Molecular Engineering at the University of Chicago, USA. He received his PhD degree in Material Science and Engineering from the Georgia Institute of Technology in 2014, and he got his bachelor's degree from Tsinghua University in 2009. And he was a postdoctoral fellow in chemical engineering at Stanford University, and he has published over 60 papers in numerous high-impact journals, including Nature Science, Nature Materials, Nature Electronics and Matter, Nature Communications, and so many. And his research group currently focuses on soft polymeric bioelectronic materials and devices as the new generation of technology, which he's going to share today. And as of November 2021, he said that his research has been cited more than, I don't know how to read it. So 10, or what is it? 16,000, right? 900 times. Wow. And then he was recognized as so many other things, and he was awarded, including this ICANX Young Scientist Award. And one thing drew my eye, especially, so he was selected as one of the MIT Technology Review 35 innovators under 35. Congratulations. So the stage is for Professor Sejeong Wang here, and
yeah, thank you very much.
Okay, thank you.
Yeah, thank you, Miso, for the very generous introduction. Let me first share my slides. Can everyone see it all right?
Yep, it's good.
Okay, yeah. Thank you very much. I really appreciate the kind invitation from ICANX for giving me this really great, fascinating opportunity to talk about what we have been working on in the past couple of years in developing new materials and device designs for new type of electronics that are built by polymers and can have various type of biomimetic nature. So today I'd like to briefly introduce why do we need this and how we can really make something different, make important advancement on this front. So if we take a look at the thing we utilize every day in our daily life, then electronics will definitely be one of the most important category, including like our cell phones, our laptops. So basically, where we were led to today is because of the past 70 years significant development of electronics that dramatically expanded our capability as human beings for obtaining various type of information for our daily life, for our communication, and also even entertainment. But if we stand as right now to further look into what could happen to the electronics technology in the next 50 years, then one projection we have is probably the functionality of electronics will have some further extension from getting information for human use to obtaining information from human body, because our human body carries so much different types of information about our health, about our thoughts. To achieve this, basically, we need to have a new category of electronics that can go on or inside of our human body to extract various type of information. But unfortunately, the current form of electronics cannot really satisfy this need because of the significant mechanical, geometric mismatch, and also chemical incompatibility with our human body. So therefore, if we want to utilize this new type of electronics to fulfill the requirements of several emerging fields, for example, including like precision medicine for human health care, and also Internet of Things, especially if we consider our human body as the most important type of things to put onto internet, and also the human robots, human machine interfacing collaborations, then we really need to renovate the current form of electronics into something that can mimic the different types of human body properties to achieve the seamless integration and even seamless merging. So the path we have been taking to achieve this new type of electronics is to use a new type of material for the electronics developments that are not conventional inorganic like a silicon-based material, but rather based on a material type that has much more close proximity with our human body, polymers. So the overall target of our research for using polymers to develop different type of human integrated electronics is to achieve those type of functionalities, including different type of stimulation and the recording from different part of our human body organs or tissues with long-term stability. So to achieve this, basically, we envision that there will be three very important aspects to develop for the electronics, including the mechanical compliance to achieve the conformable interface with the human body and the minimum mechanical invasiveness, and also the chemical compatibility so that minimum level of foreign body response will be elicited during the implantation period of those electronics. And also, the third issue is how to power those electronics and get the data when they are fully implanted. So it will need also innovations in this front. So overall, the main research directions in my group for the development of this biomimetic polymer electronics mainly include three aspects. First, we are spending a lot of effort to start from the materials level by combining different type of biomimetic properties with electronic or optoelectronic properties. And also, we dive into the deep fundamental process at the biological and the material interface to study what is the passive and active interactive mechanisms that can happen when we change the property of the materials. And the third, taking our new materials, our understandings, we further put them into various type of very useful functional devices that can really deliver the function to the human bodies. Okay, so then after this brief overview, let me first jump into the first aspect we have been spending quite a lot of effort on. That is how to minimize the mechanical mismatch between the electronics and the biological tissues. So we all know that the electronics are hard or rigid. What do we mean by hard or rigid? It's basically represented by the difference in two types of mechanical property, the stiffness or elastic modulus, and also the deformability or the maximum strain. So the materials that people have been utilized for electronics have been really sitting on the opposite ends on this mechanical spectrum with the soft biological tissues. So then this level of mechanical mismatch will cause a really big challenge for conforming the electronics to the helicobilinear and the constantly deforming human organs such as brain or heart. And even more importantly, the immunological study has found that when there is a significant size or mechanical mismatch at the interface between the implanted electronics and the surrounding human tissue, it tends to lead to repeated inflammation reaction, which will be shown as the gradual death of the functional cells, such as neuron cell, and the growth of the glia cell, which will eventually cut off the communication pathway between the electronics and the functional cell. So therefore, to solve this challenge, what we need is to change electronics, to impart electronics with the biomimetic stretchability that can better mimic the mechanical property of the human body. Then if we talk about, starting to do this, electronics is a really broad community and has a number of different sub-technology categories. So where should we start? What is the most important thing we need to work on? Actually, if we take a quick look about on the development history of electronics, then we can get very good hints. So basically, electronics are hallmarked by the developments, utilization of semiconductors, and the invention and the integration of transistors, as we can see from the past milestone events for the development history of electronics. So therefore, what we need to start is to enable the stretchability onto the semiconductors, then on the transistors. By that, we can start to achieve the real electronics. So to design stretchable transistors, it is a new direction that we need to first have an overall guidance about what are the considerations we need to have. So we all know that the transistors is a 3-terminal device that operates based on applying a gate voltage to control the on-off in the the semiconducting channel to control the current flow. So the transistors has been serving as the basic circuit elements for the integrated circuits. Therefore, to achieve the functional circuit that can deliver the type of sophisticated functionalities that we need 2 aspects to be kept on the stretchable transistor. First, it needs to have the advanced electrical performance to achieve like the high frequency operation in the circuit. And also the circuit usually needs large number of transistors. Therefore, the material and the device design also need to give the integration capability to reach the level of device density and the number of count for the sophisticated circuit design. So all those 2 aspects need to be combined with the materials to device level stretchability. So therefore, the development paths that we need to identify and follow for the stretchable transistor should have the potential of combining all these 3 very important aspects together. So from there, our vision is that a very promising path for this development will be imparting intrinsic stretchabilities from the material level onto the transistors, so that everything in the transistor can be stretchable. We don't need to like separate different things and separate different strain levels based on the difference in the stretchability. So then taking this path, we can envision that it could offer much better strain tolerance, and then more importantly, very high device density and scalable fabrication. So our major targets at this, for this development is to reinvent electronics with intrinsically stretchable materials. But do they exist, right? Our question is, if we want to do this, we need the material, but do they exist? Unfortunately, at that moment when we started to work on this, we are very handicapped by what we have in the materials front. So our overall target is to achieve the stretchable functional circuits, systems, and products. But to get there, as we mentioned, we need materials. The most important type of material is semiconductor. So for the semiconductors, everything we have a couple of years ago when we started to work on this all have very rigid properties, not to mention silicons, which will easily crack even the emerging type of polymer-based semiconductor. Because of the requirements of the high crystallinity, they still have very rigid property, cannot really deform much. So therefore, the first step we need to follow in this roadmap for developments need to be inventing new type of semiconductors that have stretchable property. Then after that, the next step we should go to is to combine all these materials to be able to create a large number of array of transistors so that we can utilize the transistor array to connect into different circuit design to realize the circuit functionality. So our second step is to address the device design and the fabrication challenge of using those new materials to develop the stretchable transistor array fabrication. And then it can start to pave the way to realize the new, real type of electronics, including different type of circuits, and finally, to get to our goal of a stretchable systems and products. Okay, so now I will start from the first part of how to combine the stretchability onto semiconductors. So to achieve this, our hypothesis is the most promising type of material should be the polymer from the electronic transport point of view. So this is because for the polymers, the charge transport in the semiconductor relies on not only the order structure, that's the charge transport from one molecule to the other through the crystalline domain, but also because of the relatively long polymer chain, it can accommodate a lot of amorphous domain so that the single polymer chain can bridge different crystalline domain across this amorphous domain. The reason that we need to look for the amorphous domain is because the stretchability basically has to come from this amorphous domain, because this will have the capability to have the chain reorient to dissipate the strain. So therefore, the conjugated polymer could give us some space to modulate the percentage and organization between the crystalline domain and the amorphous domain so that we can largely improve the mechanical stretchability without much sacrificing the charge transport property. To achieve this, it's still not a very easy task. And then the path we have been able to identify is to utilize a polymer physics phenomenon, so-called nano confinements, which basically is a nano science effect that's placed on polymers. So the way this works for our purpose is we can design this type of morphology that has a nanofiber interconnected network based on this conjugated polymer, semiconducting polymer, and then embed it in a soft elastomer matrix. So then in this morphology, the nanofiber network morphology for the conjugated polymer provides the nano confinement effect, which acts to enhance the chain dynamics means the ease of deformation of the chains in the amorphous domain, and also at the same time increase the percentage of the amorphous domain by restricting the crystallization. And then at the same time, the soft elastomer matrix will also give us the deformable soft interface that can further serve to constrain the crack propagation when the material is under deformation. So overall, this material can be simply made by blending these two components in the same solution system and just spin coating on the substrate. The autonomous phase separation process will give us the desired morphology of a conjugated polymer nanofiber network structure embedded in the soft elastomer matrix on both the top and the bottom surface of this thin film. So achieving this morphology experimentally, now we have been able to verify that indeed the stretchability gets largely enhanced by having the capability of stretching to twice of its original length, and compared to the neat state of the film without this type of nano confinement design, which will have very large crack formation. So now this so-called confined film can maintain the intact morphology up to 100% strain without any crack formation. So then if we really turn to the change of the electrical performance, so-called the charge carrier mobility of the semiconductor during the stretching process, we can see that this nano confinement design helped to achieve the 3 orders of magnitude improvement of the strain stability as compared to the neat film, basically without any decrease during the strain. And also very importantly, if we compare the initial performance without any sacrifice to the initial performance. So basically we have been able to maintain the amorphous silicon level semiconducting performance at even 100% strain deformation. So this has been our first step of achieving the high stretchability for the confined film. And then as we talk about, we presented in the roadmap, the next thing we should work on is how to utilize these new type of materials to develop the sophisticated electronics. So the key thing is to have a fabrication process for the stretchable transistor array. The reason we need to address this, although we already have all the existing microfabrication technique, you probably was start to wonder about this. It's because if we use the polymers as the key materials for the electronics fabrication, then the polymers really doesn't have the similar physical or chemical properties with the inorganic materials, which make a lot of the existing inorganic based nano or microfabrication process not really applicable to the polymers. So therefore, we have to come up with a new fabrication process that can utilize these different type of polymers to pattern them and then stack them together layer by layer into the transistor structure. So then after another years of efforts, we have been able to create this new fabrication approach that has been reported in this paper. Because for the sake of the time, I won't be able to go into the detail. So if you have the interest, you can check this paper. It has all the details about each individual fabrication process. And then eventually combining all those new material and fabrication designs, we finally have been able to achieve this fully patented intrinsically stretchable transistors that includes hundreds of transistors with a very high density. At that time, it was 2 orders of magnitude higher for the density than any stretchable transistors that has been reported. So because of the stretchability, now we can compact all the transistors without much space in between, and still be able to achieve very good stretchability. And the fabrication process is even expandable, scalable to fabricate thousands of transistors in the single batch. And then this polymer-based sheets can be attached to the human body really conformably. That's you probably don't even feel it. That's at least what I have been feeling here. So then if when we start to turn to the electrical performance that has been given by the fabrication and the functional materials we brought into the transistor array, we can see that they still maintain the similar level of mobility from what we achieved for the semiconductor that is very close to the amorphous silicon. And more importantly, the high performance we achieved was not just from one transistor, but from a large number of transistors with a high yield, over like 94% of transistors in this array, and also with really good performance uniformity among all these transistors, which basically sets the most important performance requirements for the further circuit development. And then now we can start to monitor the change of the currents when we apply the real-time deformation on the transistors, for example, during the large-scale stretching over 100% strain and the significant twisting, and also poking on some sharp object. During all this deformation, we can see that the current level has been maintained very stable without much decrease, as shown by this red current line as the drain current, and also the leakage current, which is something we don't want, also always maintained at a very low level, means that the transistor was not damaged during all this deformation process. So then, enabled by this, we further take another step by integrating the transistors in the array into some functional units. For example, the so-called active matrix that serves as the backplane for the array of functional devices, such as sensors or LEDs in the display. So the transistor basically can control the on-off for each individual functional device during the multiplexing interface. So in this demonstration, we combined our intrinsically stretchable transistors with the tactile sensor that are also intrinsically stretchable into a 10 by 10, 100 pixel array that can be laminated really conformably as the secondary skin on top of our skin, like for example, on the skin of our hand palm, to serve as the interface for mapping the physical contact of by reading the current level from each of these individual pixels on the hand palm. So basically, we can envision that this can possibly serve as the artificial skin, e-skin, for the people that have the amputees as the prosthetic skin, or for enabling the perception of on the soft robotics, which I will show a little bit later. Okay, and besides the active matrix for the functional device, we have also been able to integrate into the real circuits. For example, this amplifier circuit based on 4 transistors, and during the deformation to 100% strain, the amplification capability of the amplifier to this, you can see this black sinusoidal signal to this color signal has been maintained during the deformation process. Okay, so everything looks really promising up to here. But actually, if you are really an electrical engineer and start to take a deep, close look on what we have been achieved here, you probably will realize that there's still significant change on the current level, right? Although it's maintaining the amplification, but the gain of the amplification get changed. So what is the reason? Actually, it is because for the intrinsic stretchability on the electronics, when you deform, actually, although the materials can keep the stable performance, but you always inevitably change the geometry of the devices. For example, like this. And then the device geometry always causes changes to the device level performance, like here in the transistors. It will actually still be an influencing factor on the sophistication of the electronic performance that we can achieve. So to address this issue, another step we more recently have taken is to combine another soft material-based design that can serve to change the modulars around the transistors to much better control the strain level around the actual devices. So which we call it as a stiffening layer, elastic layer. So the way we made it work is to change this soft elastomers soft to rigid block ratio, so that it's still the same type of elastomer, but the modulus can get largely changed over 100 times. So then by doing this, we can pattern the high modulus elastomer around the devices by maintaining all the other areas using the soft elastomer. So combining this very simple stencil printing method, we can just very simply pattern this high modulus elastomer that is still stretchable around the device. So then it can help us to achieve a much better control without losing the stretchability of the devices of the transistors in the large transistor array. So after combining this design, now we can see that in this transistor array, which still has the same integration density, now when the entire transistor is deformed to 100%, the actual strain that's applied on the actual transistor is only about 15%, much less. Okay, so therefore, for the transistor in the array, compared to without this elastic layer, as you have seen, it will have some level of current change in the transistor transfer curve performance. Now it can maintain a very stable performance without almost any change in the current level. And also for the parameter of the mobility and the on currents. Okay, so taken this, we have further integrated into even more complicated circuit design. For example, this logic circuit as a NOR gate, or even like integrating 16 transistors together as a ring oscillator that converts the DC signal into the oscillating AC signal. And also for the amplifiers that we have already developed, now combining the strain insensitive design and also being able to combine like a doping mechanism onto one transistor in the circuit. Now we can both largely enhance the performance of this amplifier to achieve a much higher gain by 20 times, and also a really stable performance to the strain. And if we combine two levels of a two-stage of amplifiers together, it can even like offer hundreds of amplification to this input very small signal by amplifying to this very large signal. So now we utilizing this amplifier, we have been able to demonstrate some proof of concept applications on the human body. For example, in this case, to measure and to do the on-skin amplification of a very weak type of signal, the electromyogram from our muscle. So we can see without using any amplifier, if we only directly do the signal collection, the very weak signal will be entirely covered by the noise. We can hardly get anything. But now with this amplifier, we get very good signal quality. This amplifier on the skin is the only amplifier we utilize in the entire system. I need to mention that. Okay, so now a quick recap about what we have achieved so far on the intrinsically stretchable circuit and the transistors is that by starting from the new material developments and go to the device developments, we have been able to finally combine the high stretchability, strain insensitivity, and also the high functionality onto this new type of transistor-based electronics. Okay, but only with the transistors is not enough, because the transistors can only provide the function of data processing. But we still need the device that can help us to acquire the data and utilize the data, such as the sensors or the displays, right, in the entire stretchable system. So therefore, the next thing we have been working on to achieve this strain stretchable and also particularly the strain insensitive design is the sensors, especially the pressure sensor, which provide very important functionality for a number of different areas, for example, human-machine interface, soft robotics, and healthcare. But unfortunately, when you combine the stretchability onto the pressure sensor, you still face the same issue. That is, the strain will interfere the performance, in this case, the pressure sensing accuracy of the sensor. So as you can see in this example, from this previously reported stretchable sensor, there will be a shifting of the sensing curve when the sensor is subject to the stretching, which will cause the sensor to lose the accuracy during the stretching deformation. So this has been a really hard challenge for all the existing development of the stretchable pressure sensors. And then the way recently we have been able to address this is to create a new type of device design that can combine the stretchability as an intrinsic property still to the sensors, so that the sensor can have very good conformability deformed together on the skin, but have been able to achieve, as we have shown here, like an unaltered pressure sensing performance during the stretching to this level of a large deformation, 50% strain. So how did we achieve this? So the new device designs that we have created to counter the influence of the strain, the stretching on the pressure sensing performance are by combining two important aspects. Okay, first, so we have created a pressure sensing mechanism based on a soft ionic elastomer. So that's the capacitor it built is only given by this very small contact between this pyramid structure and the top electrode. So therefore, when we need to control the strain's influence, now the target is to only control the geometry of these very small areas between this contact interface. Okay, that's our first key aspect of the design. Okay, so then how to control this small interface? So what we have further added into our device is those mechanical hierarchical microstructure underneath this micro pyramid structure as the part of the electrode. So then basically the local stiffness of this pyramid electrode gets largely increased. So then from this design, during the deformation, the stretching, each of these pyramids will not change much. Therefore, the interface that determines the capacitive reading of the pressure sensor will also not change much during the stretching, but will only correspond to the respond to the pressure information when the entire sensor is under pressure. Okay, so then from this, we have also combined the finite element simulation to verify that indeed this is the case that we have hypothesized during the deformation of the stretching. The response curve of this contact area at this pyramid tip is maintaining the same relationship to the pressure, which indicate that the sensing performance should be unaltered under the deformation. So further, we have fabricated a number of devices based on this design, and as we can see that indeed the pressure, the strain intensity performance have been achieved, and more importantly, it's not only from one sensors. We have tested multiple sensors and put all these performance together. We can see that they overlap very well with each other, right? With a very high robustness and a high strain sensitive performance. And also the sensor still can provide a very fast response with a less than 50 milliseconds response time. So basically, seeing this performance, now we can confidently say that compared to all the reported stretchable transistors, so we have been the first type of device that have been able to achieve the combination of three very important performance metrics, including the sensitivity, as shown by the limit of detection, the stretchability as shown by the working strain, and also the high strain insensitivity. Okay, so then to give some projection of how this can be possibly useful, we have further integrated into the soft robotic applications, particularly for the application scenario of the remote remote medical therapy or diagnosis, right? Like for example, in the current case of COVID, in a lot of cases, we really have the restriction of like going to the hospital in person. So if the doctors can do some remote diagnosis or simple treatments by utilizing the like robotic intelligent robotic technique, then a lot of things actually can be done at home. So by combining the soft sensors onto the robotic hand will be an important step to achieve this. Like for example, in this case, the soft robotic hand integrating with the sensors can achieve like a good control, a closed loop control of the pressure level by itself when it's when it's touching the human arm. So for the sake of time, I would just directly skip this video and go to this one. So this is really showing how we can utilize this stretchable sensor to realize the remote medical diagnosis, like the measurement of pulse. Right? For measuring the pulse in the right way, the robotic hand, as you can see, need to deform. The deformation will cause the strain on the sensor. But because of the strain in sensor performance, the sensor signal was not changed. It only starts to change when the sensor gets onto the human body when there is a pressure, and then start to like record the pulse waveform from the very subtle pressure change from the pulse. So we can see that the very high quality reading has been able to acquired from this robotic hands sensorized interface. Okay, so this has shown basically in this part how our designs can possibly utilize a polymer as a platform to combine the stretchability with the semiconducting or conducting property. But this is still not enough, right? For the human integrated, like biomimetic electronics, we still need other aspects of biomimetic properties, like immune compatible property, biosensing property, so on and so forth. So therefore, to achieve this, the material design need to be further expanded into new structures that possibly need to incorporate other non-conventional units to achieve those new type of functionalities. So then one obvious path, a possibility for those new type of chemical design is to, like, for example, integrate those new functional units onto the side chains of the polymers. But actually, from the synthetic point of view, this is quite challenging because all the existing synthetic paths for the conjugated polymer has been following synthesizing the monomer with the target state structure first, and then polymerize at the ends for the last step. So therefore, it caused significant limitations. So then more recently, we have designed like a paradigm shifting synthesized approach of first making a polymer precursor as a universal structure with a reactive group at the end. Then using this universal polymer design, we can put on like almost any type of chemical structure function unit by just one step synthesis, very simple, onto the side chain. So this can be carried out both in the solution for realizing the bulk modifications throughout the entire film after the spin coating, or on the spin coated film only as a surface modification. So we have demonstrated that using this design, the performance is well maintained, both for the bulk functionalization that changed the polymer structure entirely, or only on the surface of the thin film with even less influence on the performance. Okay, so then by combining this, we have demonstrated two possibilities of realizing new functionalities in this current work. So first, we have integrated a photoreactive group, photo cross-linkable group onto the side chain, which is would be not possible if we first put on this group and then finally polymerize, because this will react. But now, for putting this group in the last step, it can be compatibly integrated into the polymer design, which allow the direct photo patterning of the polymer, just one step photo patterning by cross-linking it, and then still maintaining the unsacrificed performance when we use the solution to solvent to dissolve the uncross-linked part. And then also we have been able to realize the biosensing, intrinsic biosensing function by just directly functionalize a protein onto the side chain, covalently functionalize the protein as an enzyme onto the side chain to realize the targeted sensing for the glucose when it's present in the solution. So basically the glucose will cause the redox reaction in the conjugated polymer to change the current level from the sensor reading. Okay, so with all these, now I like to close my talk by saying that hopefully we have shown that the new material and device design, synthesis, and fabrication concepts can really enable this new type of biomimetic electronics that combine different type of devices, semiconductors with the stretchability and also multifunctional properties. Okay, so at the end, we are really optimistic that it will be, we will go into a new era of this so-called electronics and the human body nexus built upon a range of different materials, devices, and have broad application merits. So I'd like to thank all my students and the funding agency and the collaborations for making this work possible. And then at the end, Happy Chinese New Year that's going to come just in a few days to everyone. Okay, thank you very much.
Thank you. Thank you for your talk and fantastic talk from both of you. So now we're going to go into the panel discussion. So I will invite both of you and Professor Miso Kim and Professor Ari Zhang to join us for the panel.
Okay, maybe I go first for the questions. I'd be challenger. Yeah.
Sure.
So normally we have a challenger to ask the first questions. This time I like to challenge these two young scientists. Yeah, they are both superstars. First is go to Sejeong Kim. Sejeong, you have in the last part of your talk, you say you develop a new method to remove, no replace for the implanter, right? Yeah. But for the implanter, though, it's very heavy and traditional, old kind of equipment. So, but it has really some kind of good things because it can be controlled very well. It can be controlled, even the depth and the dosage, all these things. But in your method, is that possible control, very well or precisionally like that?
Yeah, that's a very good question. Your implanter is already well-developed equipment, so it's kind of hard to substitute implanter to a new method. So I think our method is more focused on how to make it more simplified in terms of fabrication method. So if we want to create an array, then for implanter, we always need the mask. So we open the holes and then we use implanter to create the whole array sample. So the first advantage is that we can remove that masking step. And as you asked, so the depth is actually really important when we implant the ion. One thing we discover is that if we change the ion, so for example, in our case, we use xenon, but you can also use gallium or helium ion, for example. So that also changes the depth of your implantation using focused ion beam. So using our method, we can also control the depth of implantation.
Okay, thank you very much. Very good. Yeah. So for Sihong, I also have one question. I think you really, run too fast. Yeah, build up so many things. I have one question is, for the kind of a flexible devices all you made, how you to avoid all that kind of problem from the kind of humidity, temperature, this kind of effect. Yeah.
Yeah. So this is a really great question. Indeed, the materials we have been using, as a, the polymer semiconductors, intrinsically, they are not very good to the like humid or like a human body environment, but mostly similar to the conventional electronics. When you use those like functional materials and the devices, you would encapsulate them. So then it will largely rely on having a reliable encapsulation layer that can prevent any possible penetration of the moisture into the inner device. So then that should, very well separates the polymer semiconductor with the humidity. And then on the other hand, another thing I show at the end is to directly use the polymer to interface with the human body fluidic environment as a biosensor, right? So then in that case, of course, we cannot encapsulate. Actually, people have spent also quite a lot of efforts in developing a new type of transistor that's open to the electrolyte or biofluid environment, so-called organic electrochemical transistors. Then the influence of humidity, mostly on the partial doping of the semiconductor, actually is taken as an advantage of enabling the on-off operation of the transistor, and then further realize the sensing performance. So, just as a one sentence summarize, if, for that kind of application, some moderate level of doping from the humidity actually is something useful. So then regarding the temperature issue, although the semiconductor based on polymer cannot go to like 200 or 300 degrees C, but for the application direction, that's we are mainly developing this for, like integrating with human body. Our temperature is relatively stable, right? So we are all usually given mild temperature, so it won't, in this application direction, cause like a special challenge to the semiconductor.
Okay, thank you very much.
Yeah, thank you, Alice, for the question.
Thank you very much. Actually, can I follow up on that question?
Yes, of course.
Yeah, because the temperature is stable, but when it comes to polymer, they absorb a lot of organic volatiles. And human beings, our body chemistry is very different, right? So some people are using perfumes. We are emitting all sorts of organic. Do you anticipate there'll be need to control surface diffusion of organic molecules in this kind of flexible electronics?
Yeah, this is a really great question. On one hand, actually, the permeation capability of the polymers could be an advantage, and actually is an advantage. We recently have spent a lot of effort to actually explore, is to increase the interfacing effective area between the functional device and the human body, like the bioelectrolyte. Because if you have only inorganic material, then the interface only happen at the very surface. But now with the capability of having like biofluids, including the analytes, to further diffuse into the polymer network, so then you are actually extending the surface interfacing into the bulk interfacing. Then any type of like analytes concentration change will be much more sensitive to be like collected by the this material and the overall device structure. But then whether that's following your question will be a stability issue, I would admit it could be possible, right? But the good thing is that in the human body, we basically have two types of organics. One is a polymer. They are usually not soluble, like proteins. And then for the soluble, like small molecules, they still have relatively large size. And then also there won't be much chemical like interaction pathways with the conjugated polymer. So therefore, we probably can stay relatively optimistic that it won't be a major issue, but it definitely needs further like a careful investigation. Thank you.
Very good. Any other question?
Yeah, I have one for Sihong. So I was always wondering about the mass production possibility of the flexible devices. So these days I can see like every day there is a new report on very fancy flexible devices, stretchable device in nature and nature materials and everywhere. So I've been always wondering about the mass production possibility. Do you expect like something that can happen like in the very near future, or do you have any challenges or something?
Yeah, this is a really great question. Mass fabrication is, one of the key requirements for any type of electronics to become useful. And from, part of the work I have shown, you probably have seen part of our effort was focusing on developing a new fabrication process, right? Although it's still like an academic stage fabrication, but it does have the potential to lead to the mass manufacturing. We have demonstrated that possibility a little bit by fabricating thousands of transistors together. And then another thing I also need to mention is, for this intrinsic stretchable type of electronics, it's largely built upon polymer electronics. And then if you take a look at the development path of polymer electronics, another avenue people have also put a lot of effort is a printed electronics to use like additive manufacturing, for example, inkjet printing or roll-to-roll printing, to actually scale up the fabrication process beyond what's the wafer-based silicon fabrication can achieve. So then I think that will be a very natural combination that can happen along the way for this developments to actually take this advantage to realize real mass production of the polymer-based intrinsic stretchable biomimetic electronics. And I think in the near future, some of the products could be commercialized and go into people's everyday life. Thank you for the question.
I think this question also can go to Sejeong. Yeah, for you materials and all this. How about your ideas?
I'm sorry, can you repeat the question again?
I think this question, the same question for mass production, also for you.
Oh, yeah, that's very challenging, and that's very good question for me as well. So yeah, mass production is challenging, especially a lot of 2D material applications. Still, we use transfer technique in laboratory. So ideally, we can develop a way to create 2D materials using CVD, which is working well nowadays. But there are some advantages of using exfoliation technique, because you can get very high quality crystal very easily, and the crystal domain is much larger if you use exfoliation technique. But I know that CVD technique is also developing very quickly. So for example, for HMAN crystals, there was a paper from, I think it was from SKKU, where Miso Kim is right now. So they actually developed a method to create monolayer and single crystalline monolayer wafer scale HMAN layer. This was published in Science a few years back. So this is very important for us, because it means that we can bring our technology more toward the practical devices. So I think it is also promising for our applications as well.
Oh, SKKU has the best lab of material science.
Yeah.
So Miso, you are.
Yeah.
Very great.
Very good. Can I ask one more question? Following up that question on the scale up, one of the things that I was very curious about when it comes to single photon emitters, what is your sensitivity to surface structure? Because you have to fabricate this very fine structure. When I can imagine if the interfaces are not very smooth, then your noise is going to scale with smoothness. If we start thinking now, not just about the material, the 2D material itself, but the cavity that you need and all the support structures to be able to harvest this single photon, how much noise are you going to get from the nature of the interface? And how do we encourage the young people to not see all the noise, but see the beauty in the science? So what is happening in terms of interface engineering to mitigate noise and bring more accuracy to this quantum electronics?
Yeah, that's very good question. So for quantum emitters, I think it depends. Sometimes we get so you're talking about the surface defects, right?
Yes, because you have to mail it, and if you mail it, I'm assuming you're using something like a FIB or ion etching, reactive ion etching. So those interfaces are not going to be as smooth as a crystal lattice, right? So they have defects, right? And then you have a lot of the debris that will come from the processing. And if you're getting a single photon that you want to be harvested and captured, how sensitive are you to those defects? And how much does that translate to noise in your device?
Right. Yeah, so now I get it. So yeah, that's a very good question. And for single photon emitters, we can actually mitigate this problem. So if you imagine a quantum emitter in monolayer HBN, then or a few layer samples, then we have problems from the surface state and surface defects, because the emitter itself and surface defects are very close. So we can easily, our sample can damage from these signals. But the advantage of using HBN is we can use thick layer sample. So imagine you have like 100 nanometer sample and your emitter is inside in the middle. So your surface states are very far. So we don't really affect by this noise.
Okay.
So that's one thing for quantum emitters. And for photonic devices, when we fabricate using FIB, then we have very rough surface. And luckily for photonic devices, this roughness is less than the wavelength scale. So the wavelength doesn't really affected by this small roughness at the surface. So I think we can still avoid these problems in integration. Thank you for your question.
Yep. Maybe I don't want to hog the microphone, but I just want to ask one more question to both of you. You presented very advanced, very sophisticated work, right? There are a lot of students out there watching this talk or who will watch this recorded talk, and they look at it and they say, holy moly, there's no way I'm going to understand this. So how do you encourage them to get into this field? Because especially once you get into device fabrications, there are students who are very good in the fundamental science, who are also not very good in the fabrication. But there are some who are very good in the fabrication, but they're not very good in the science. But you two have been able to bring the two together. How do we encourage the students, the young scientists who are coming up, to not be afraid and to venture into these very integrated fields?
I think this is a really good question. Maybe can I start first, Sejeong?
Sure. Yeah, sure.
Yeah, this field is definitely multidisciplinary, and it doesn't mean that you have to be good at each and every field. For example, for me, it's part of quantum physics, quantum photonics, and part of nanofabrication, and some of engineering, and some of material science. But when I first started, I was more like a experimental physicist, but I wasn't very confident in quantum physics, for example. It was one of the subjects I didn't like very much. So I was a little bit afraid of starting this research field, but I think by doing experiment, I can get better feeling of what's going on in quantum photonics. So if you think that if students think that they're good at one specific field, they can jump into this field and they will slowly get better at other fields. And one last advice will be, I think everyone feels a little afraid when they first started. I don't think like there's anyone who feels confident that they can do this field very well from the beginning. So it's okay to feel little intimidated when you first started. So yeah, I think that will be my advice. I will toss this question to Sihong.
Yeah. So first, I really echo everything Sanjay has said, right? So those are all really great advices, and Martin, you are describing exact same feeling I keep getting again and again when I'm going to other talks outside of my field, right? Overall, always there could be a lot of unfamiliar information, and the overall topic may seem interest, but if you really want to go into more details, then there will be some barriers standing in front of you. But overall, I think what's the most important for doing research is number one, what's really drive you in making great progress is your interest. If you find something really interesting, then you will have enough passion and make enough effort to overcome all these barriers. And then second, doing research is also a learning process. You don't really need to know everything before you start to do research, right? When you get into a new field, like what Sanjay has said, you often start to work on one thing, start from one particular small topic. And then while you're working on this, your knowledge scope is getting very fast, very rapidly expanded. Then you will start to get to know more about other related topics, and then have the capability of addressing other challenges. And then the ultimate benefits to everyone working in this kind of interdisciplinary field is you will be able to get a really interdisciplinary training. Then after working in this field for a period of time, you'll be able to really get equipped with all the different knowledge base and the techniques.
Okay.
Thank you.
Hi, Martin. May I ask one question? Is from one shy boy. Yeah, it's sending a message to me because he's now looking for a faculty job, but it's hard to get it. So yeah, he want to ask what's a secret for you guys, to get such a good faculty job. Did you get any secret to share? Sihong,
Yeah, I was
maybe.
also looking for that secret a couple of years ago, but seems like I didn't really find a very unique secret. I think eventually, although looking for a faculty position at this career stage is a very important thing, but you just have to remember, right? Your ultimate intention is to do research. Then if you always think about that and make very good research product, then you will definitely get the payoff, right? It sometimes pay off better, sometimes pay off less, but it won't stop you from making further very important discoveries.
Okay,
so I think just keep learning, keep
learning, get a publication, right? Get high impact.
Then you will just naturally get where you desire to go.
Okay, so Sanjay, did you have any secret? And especially for the young lady, yeah.
Yeah, I think this is really good question because this was what I've been thinking for my 6 years postdoc. I actually did my postdoc pretty longer than other people. And I think one of the things that I thought was because I got my PhD in South Korea, and I knew that getting a professor job is pretty competitive and it's very, very difficult. So by the time I finished my PhD, I decided to maybe try out because Korea has a limited number of universities, but if you decide to go overseas, then there are more opportunities. So what I decided I'll go to Australia first, and then I learn English, and then I have more opportunity to get a job because once you are once you can speak English, basically you can apply for any other universities in the world. And then I started to feel a little more safe because now I can apply all the universities in the world. So I think that's one of my advice. So if you're based in one country, now you can actually look around. There are other universities in all over the world where you can go, and that's one thing. And then just briefly, second, since I'm in Australia, and each country has different things that require for professor position. For example, when I first came to Australia, I think one of the important things is how you can network to other people in other universities. So networking was one really important thing. It shows that you can collaborate to people. You're not a person who works alone. And another thing is global leadership. So for example, like what here, like Alice and Miso and Martin, everyone's global leaders here. It's just like that you start involved in some global community and you start the leadership role. And that was one of the other important things to show when you apply for faculty position. And I call myself more introvert, not extrovert. So taking on the leadership role wasn't in my comfort zone. So I have to really step out of my comfort zone to apply for like committee positions and all the other global positions, which I actually do a lot these days. But that was definitely something out of my comfort zone. So if you're applying for other faculty positions, you can actually see what other young professors are doing now. And those are the things that you want to build up and include in your CV. So yeah, that's my advice.
Wow, very, very nice. Very helpful. Actually, Sanju, your experience is very helpful because the question was asked by all of my previous students. He is, really want to get a faculty job, but now in China, it's like roll to roll. Right? Printing, so it's too tough. The same as Korea, maybe worse. So yeah, you open the the mind and you open the window. I think he should consider to go other place, right? Yeah, not get here like every day get it. Yeah. So very good.
Yeah.
Sihong, did you have anything to add?
Yeah, maybe what I also can give as a advice to a little bit earlier stage students is, although for applying for faculty position is a kind of a competition, right? People look at everyone's achievements, everyone's potential, but eventually coming down to like two different persons, kind of comparing apple to pear, right? They are like mostly working in different fields. So then what's very important to get like kind of as a secret to get you more opportunities to be considered is to choose the right field to work in. Because not every field is treated the same when they are on the faculty market. Because for like if you are in a rising field, then it means on the funding level, there will be more funding opportunities. Then it will come down to more faculty positions. And of course, for like a researcher, it will also means you can have more opportunity to make important discoveries, achievements in the future. So then when you like for example, apply to PhD position or apply to postdoc position, you really want to, be very careful about what is the thing you are interested in and what are the things that can have a tremendous growth future in the next couple of years, not just at this right moment, because the time you probably will apply for the faculty position will be a couple of years after you enter the field. So you need to have a kind of a forward looking, maybe sometimes like Sanju mentioned networking, right? If I'm not sure, talking with someone else, more experienced, like mentors, then you probably will have some very useful suggestions.
Cool. Thank you. Yeah, for all this nice sharing. I think the listener audience will have more kind of opportunities. Yeah. Okay, Martin. Yeah.
Very good. Thank you so much for your presentations. We really appreciate finding time to come and share your science. And I'll hand it over to Miso to take over the next step.
Okay, this will be the highlight of our today's session. So I'd like to deliver certificates to our outstanding, amazing speakers today. So the first certificate goes to Professor Sejeong Kim. Congratulations, and we are so proud of you. And I'm so happy that I have a chance to deliver this certificate to you. Thank you. Congratulations.
Thank you.
And the next one, again, the same thing, amazing work, and then amazing talk today. So the next, can you, okay, we need to go to the next page. So, because I would like to deliver the certificate to Professor Sejeong Wang as well. So, and the second, but it doesn't mean the second part. So you are, we have our top priority for both of you. So thank you so much, and we are so proud of you. And I'd like to deliver this certificate to you. And Alice will give deliver the certificate by email later. And then today, this is just on the screen. So thank you very much, and big congratulations again.
Yeah, thank you very much.
Okay, great. Yeah. So today our show is so nice. We hear wonderful talk,
Wonderful experience sharings. And as Sihong said in his last slides, that will be Chinese New Year. So, so I have to deliver something new for this, I can act the tax. So today, as I'm going to deliver or announce this, I can act the tax 2022, the calendar. So this year we already have 4 coordinators from all over the world. Me, Paul, Fulan, and Martin. Yeah, you all saw them on the stage already. But in the coming year, you will see them often and often because we already have the full schedule. And January, we already have 3 weeks. The first week is from Professor Ren Zhifeng. Second week is Constantinian. And this week was 2 young scientists, superstars, Sihong and Sejeong. This was January. The title and the topic we focus is nanomaterials. And after Chinese New Year, we will have the March session from February 25th. We will focus on the applied nanotechnologies. We will have speakers, Chad Merkin from Northwestern University, and we will have Paulo Samori was from France, Strasbourg. And March 8, we will have a global female scientists go together to celebrate for the roles in science. And then afterwards, we will have Justin Hannes from Johns Hopkins. Then we'll have Sam Kim from SKKU. Then we have Jianping Gong was from Hokkaido University. And all this will focus on the topic about applied nanotechnology. And at April, we'll have biomaterials and applications. We have April 1st as our Xianting Ding and Flower was our young scientist winner. And all of them are superstars too. And April 8, we have Fulan, and then we have Rashid from UIUC. And April 22, we have Li Ju, was from MIT. All of the topic of the biomaterials and applications. And the end of April, we'll have a special session for the Spring Summit. So we invited many famous professors here. Jean-Pierre Savage was Nobel laureate in 2016 from Strasbourg, and we have Stephen Hill was from Max Planck. He was a Nobel Prize. He won the Nobel Prize in 2014, and we have Professor Gang Chen from MIT. And we have Professor Jack Dish was from Australian National University, and is going to be the president of Australian Academy. Also our previous, coordinator here. David Leahy was from UK University of Manchester, and Li Hong Wang was from Caltech. And we have Mix, Anthony Mix was from Rice University. So many, famous stars will get on this Spring Summit. I just put some examples here. So please follow us on this big event. And May we will have light and energy. We invited Pei Si Li was from Nanyang Technology University. We have Harvard and Wang Fan, our young scientist stars. We have Manish was from University of Cambridge. We have Walter Harry was from Caltech too, Caltech. And then in June, we will have our 100 volumes celebration. It's June 2nd. We have Cherry Kagan from UPenn. Then we will have Hale Apple was from Texas and Austin. We have Chao Yang Lu was from China. We have Yuan was from Arizona. And we are so happy. And this month we will have 100 and beyond. And July, we will have 5 weeks, many topics. Patrick was from Paris, and Heidi and Deep was our Young Scientist Award, and Chiu Min was from West Lake University, and we have Martinez was from Argentina, and we have Taki Lee was from Seoul National University, and this month, July, will focus is across nano divided. And August, we will have Wang Yingxiao was from University of South California. We'll have Joan Foster was from UBC, Canada. We will have Lian Zhou Wang was from University of Queensland, Australia. We have Chaplin was from South Africa, University of Cape Town. So this August, our topic is bioengineering. All of them were famous bioengineering scientists. So looking forward to that. And September, we'll have a very special month because we invited many famous stars, not only in science, also all of them are superstars and super teachers. Professor Zhi Gangsuo was from Harvard University. Everyone know him, and not only a super scientist, also the best speaker. And Professor Nicholas Peppers from University of Texas and Austin. He has nursing more than 1,000 students. So we will have this celebration for him on the stage for the Teachers' Day. We will have Santi Kim from Hanyang University. Arika was from Washington, Seattle. They are our ex-young scientists. We have Annie was from University of Melbourne. Was from Australia. We have Brad Nielsen was from Switzerland, ETH Zurich. All of them will talk more of beyond the science, not only science, also many secret of nursing students and the high tech. And October we'll have Shining Light because October is a big celebration month in China and in all over the world. And October 7th we will have the 70 years anniversary of Huazhong University of Science and Technology because it's my alma mater. My university, I got my PhD there. So it will be a big celebration. And October 14 and 21, we will have a light rising star selection on the stage. And in the last week of October, we'll have Martin Wagner. He's from KIT, from German. Everyone, if you have ever listened to his talk, you will remember he has the best artist taste of the PPT, and of course his 3D printing work was so beautiful. Yeah, looking forward to that shining light on ICANX in October. And in November, we will focus on the soft matters. We have Australian National University superstar was Dragneel Natural. We will have University of Toronto superstar Aaron Vo. We'll have Adam from University of Edinburgh. We'll have Chi Bingpei from UCLA. So all of them did many fantastic works in the soft matters and the soft electronics and the soft robots, all these things. Yeah, let's celebrate for this. And in November, we listen to their latest work. And December is our Young Scientist Award selection comeback. Yeah, so we will select for the next 2022's Young Scientist Award. So we will have a big celebration, and in the end of this of ICANX, December 16 is our summit. So that's all of this year's schedule. And here I gave you this one as our calendar. So you will receive that calendar on ICANX on the website. Also will send the email to you. You will see everyone. You can mark on your calendar which one you want to follow. And this was a whole bunch of our talk in 2022. So let's celebrate the Chinese New Year. So during between this from tomorrow and 3 weeks, we'll have a big break. So celebrate our holidays of Spring Festival. After that, February 25th, come back to ICANX. Then we have a bunch of fantastic talks for you. And I hope you can join this international community and you also can contribute to this, community. You're welcome to be panelists. You can send an email to us. You're welcome to be challengers. And also you're welcome to be speakers. You also send the email to us, and we want to have you here, and we want to have everyone here because ICANX is connect world and universe. We hope everyone happy on this stage, and we hope everyone have a fantastic new year, a tiger year. Thank you. See you next year.